Hello there. This tutorial will take you through a solution to a problem of Kirchhoff's using simultaneous equations. In particular, we're looking at a problem where you have a circuit with two voltage sources. Now, to solve this, there's any number of ways. Kirchhoff's is just one of them, and I'll take you through step by step. If you want to follow along, you can either write it out longhand, or you can go to the website and look up Kirchhoff's problem 1, and you can get a PDF of the problem sheet to actually fill in as we go through. Right, so how do we get started? Well, we're going to use Kirchhoff's, and there are two laws that we can use to help us solve the problem. Kirchhoff's first law, also known as the current law, says that the sum of the currents going into any point on the circuit, any node on the circuit, will equal the sum of all the currents flowing out of that node. So let's have a look at the one at the top here and see if we can identify the various currents going in. We're going to make an assumption about which way the currents flow. It doesn't really matter which way we choose as long as we stick with that for the rest of the calculation. So let's stick some possible current directions in. If we start with the voltage supply on the left hand side, the current flowing through the circuit due to that power supply is likely to go in this direction. Okay, so the first current we're going to write on our diagram is I1, which is the current due to the voltage supply there. Similarly, if we look at the second voltage supply, it's fair to assume that the current due to that voltage supply will go in this direction. So we actually have two currents going into that node, which means that the third current down this leg must be the sum of those two going in. So the first equation we're going to get, due to Kirchhoff's first law, is that I1 and I2 equal I3. The sum of the currents going in equals the sum of the currents going out. Here we have I3 equals I1 plus I2. Kirchhoff's second law, also known as Kirchhoff's voltage law, states that for any path in a circuit, the sum of the EMFs equals the sum of the PDs. So when we look at this, the EMF replies to the electromotive force, the force that actually pushes the current around the circuit. So any voltage supply is an EMF. The PD is the potential difference across the components in the circuit. So in this case, a current wouldn't flow through that resistor unless there was a potential difference. In other words, the voltage at this side was greater than the voltage at this side. So the potential difference is the voltage drop across the components in the circuit. To help us put this into an equation, then we need to calculate the PDs. So here we have the resistance value and we have the current. So we can actually use Ohm's law to find the voltage drop, because V equals IR. In this circuit we have three paths around the circuit. For the sake of solving this, we're just going to look at two of the paths, one due to voltage 1 in this area and the other one due to voltage 2 in this part of the circuit. So we can follow what we're doing. We'll label the two paths that we're going to consider loop 1 and loop 2, and in each case we're going to look at Kirchhoff's second law. So whenever you're solving any of these problems, it really is worthwhile writing down each step, so that if you make a mistake you can go back and identify where you've gone wrong. So for loop 1 we're going to use Kirchhoff's second law. The sum of the EMFs equals the sum of the PDs, and we're going to substitute in the values from loop 1. So the EMF is 5 volts and the voltage drop across R1 is You can either write it down as I1 times 12 or 12 times I1, it doesn't really matter, but we're going to do this because it will simplify it later on. So 12 is the resistance, I1 is the current, and flowing through R3 we have 20 ohms times I3, and that's our first equation for loop 1. Next we're going to do the same for loop 2, exactly the same. So let's write down what we would get for Kirchhoff's second law going around loop 2. In loop 2 we have an EMF of 10 volts. We get 10 equals 15I2 plus 20I3, and this is our second equation. Now we have two equations, and you can see it's starting to look like a simultaneous equation. The only difficulty is in these two equations we have I1, I2 and I3, so we have three unknown values in two equations, which means we can't actually in that form use simultaneous equations to solve it. However, we do know that I3 is equal to I1 plus I2. So if we substitute for I3 in both those equations, we then have two unknowns, I1 and I2. So let's move on and do that. Again, I would recommend you write down everything you're doing just to make it easier to look back on it afterwards, and also to see where you could possibly have made a mistake. So we're going to substitute first for I3 in equation 1. So we replace the I3 with I1 plus I2, and then we can multiply that out and simplify. So we get 5 equals 12I1 plus 20I1 plus 20I2. And again we can simplify that further by adding together the two I1 terms. So we end up with 5 equals 32 I1 plus 20 I2, and we're going to call that one equation 3. From equation 2 we get 10 equals 15 I2 plus 20 I1 plus I2. And again we can simplify by first of all multiplying out the brackets and then collecting together the similar terms. So here we have 15 I2 and 20 I2, so we can bring those together, and getting 10 equals 35 I2 plus 20 I1. Now when it comes to using simultaneous equations, it's helpful if we have the I1 terms over each other and the I2 terms over each other, so we can actually see what we're doing. Makes life a little bit simpler. So let's just swap those around, and the result is we have two simultaneous equations. 5 equals 32 I1 plus 20 I2 and 10 equals 20 I1 plus 35 I2. So the next step is to make sure that the number in front of the I1 terms is the same in both equations, or the number in front of the I2 terms is the same in both equations, so that we can actually then cancel them out. And it doesn't really matter how you do this. You can actually multiply this one by 32 and this one by 20, see, to make sure they're the same, or you can use decimal values, multiply one by decimal value, so you're only multiplying out one equation. For the sake of simplicity, I'm just going to multiply this one by 20 and this one by 35, so the I1 terms will then cancel out. Again, write it down so you can see what exactly you're doing. So we're going to multiply equation 3 by 20, so we end up with 20 times that, multiply them out, 100 equals 640 I1 plus 400 I2. Equation 4 times 32, we get 320 equals 640 I1 plus 1120 I2. So the I1 terms will now cancel out, and I suggest what we do is we subtract this equation from this one. We get 220 equals 720 I2. Then we can calculate I2. I2 equals 220 divided by 720, which gives us 0.305 amps or 305 milliamps. Now we've got I2, we can substitute back into any of the equations above to actually determine another value. I'm going to put it into equation 3. Equation 3 gives us 5 equals 32I1 plus 20I2, so we're just going to put in that value for I2 so we can actually calculate what I1 is. We get 5 equals 32I1 plus 20 times 0.305, which simplifies to 5 equals 32I1 plus 6.1. Therefore 5 minus 6.1 over 32 equals I1, and again we can simplify that to get I1 equals minus 0.034 amps or minus 34 milliamps. The minus sign, the negative value, actually indicates that when we first drew in the arrows for the direction of the current flow, the direction we chose for I1 was actually in the wrong direction. It's not an incorrect value, it just means it goes in the opposite direction to what we originally chose. So I1 in actual fact flows in the opposite direction. So now we have I1 and we have I2. We can substitute those into the equation we got from Kirchhoff's first law to determine the current value for I3. And again, it doesn't matter that we have a negative value in there, we stick the negative value into the equation. I3 equals minus 34 milliamps plus 305 milliamps, which gives us a value for I3 of 271 milliamps. All we need to do now is just go back to our first diagram and look at the directions of the current flow so that we can amend those. In our original diagram we'd assumed that I2 was flowing in this direction, and because we've got a positive value that was a correct choice. In our original diagram we'd assumed that I1 was flowing in this direction, but as we've got a negative value, then in actual fact that was incorrect. In actual fact I1 is flowing towards the V1 power supply and not away from it. That just leaves us with I3. In the original diagram we'd assumed that I3 was flowing down, and in actual fact that's correct because the value is there positive, so we've actually got 271 milliamps flowing down. Okay, so that's that problem solved.